Okay, so welcome to the first MRI part of the course for lecture. Before we begin, any general course questions about logistics or anything that's coming up? Okay. Yes, was there a question? Yeah.
For the presentations, is it like a background presentation about like our topic and like what we did, or is it like if we're doing a coding assignment, we're like walking through kind of how we did things?
Yeah, so in the time you have, you don't really have you have to sort of split the time up. So I would suggest just providing enough background so people can follow what you're doing. Obviously, a deep dive into the code is also not practical. So you sort of have to, maybe walk through what you were trying to do with the code. If there were some interesting things you did, you could talk about them, but more, a little bit of both. So Professor McVeigh and I, as we're looking at the presentations and scoring them, essentially, we look for how clearly you presented things. Is it related to the course material? That's actually something to take into account. For example, if you in past years, if a group comes in and all they did was like machine learning and it required no prior knowledge of the course, then that doesn't really get very good points in terms of relevance to the course, right? If you could have done basically one check is if you could get done the project without taking the course, then it doesn't really fit in with the course. So like a pure machine learning or deep learning project, you have to relate it to the course. The other thing is the other major distinction is difficulty score. That's 10 points, but that tends to be the main differentiator between groups. That's the most dynamic range. So if your presentation is simply a review of the material, that doesn't get very high difficulty scores. If you've implemented your own recon and showed that it works and everything, then that tends to score fairly high in difficulty. And in between, you don't kill yourself over the project. Do your best, make it something that you're interested in and helps with your learning process. But that just sort of gives you a sort of guide to what we tend to look for. Yeah. Any other questions? Yes.
Are well covered by the section of the textbook. Can we just cite the pages rather than many words and have to go back up everything to explain them?
Yeah, I mean, I think we don't necessarily, you can't, we certainly don't want, like in the time for a presentation, you just have to present things clearly. If there's a result that has already been derived, you don't need to rederive it. But certainly, you don't want to just have 3 slides listing what was in the book, right? That's also not interesting either. So just, I think you all have seen good presentations and you've all seen bad presentations. So just use that experience to make your presentation a little better. All right. Okay. So any other course logistic questions before we start the content? Okay. So we're going to start MRI today. And we're going to go over sort of these key concepts. Let me sort of there we go. So these are the sections in the book that are sort of related. We're not going to go exactly the way the book goes, but we're going to cover, sort of what an MRI system looks like. And then hopefully today we'll get into spin and magnetization, precession, RF excitation. That's probably as far as we'll get today, but if we have time, we'll go on to the other topics as well. And the idea behind the MRI portion of the course is there's a lot of material. So we're going to go through quite a lot of material. Because MRI is a fairly complicated technology. Okay. So this is what a basic MRI system looks like. There's 3 main coils you really need to know about for MRI. The first is the magnet. Okay. So all MRI machines have a magnet. And in some MRI machines, this magnet can be fairly large, and we'll talk about how large that magnet is, okay? The second coil is the radio frequency coil, and that tends to be the smallest and lightest coil. That is the coil that transmits energy into the subject or into your object, and then it also listens for the signal back. So it's a 2-way. So that's how you're actually getting the signal both into your object, putting energy into your object and listening for the reflections or the vibrations coming out, okay? The third coil is the gradient coil. And that is also changed the magnetic fields. And the job of that coil is to create variations in the magnetic field. And it's those variations in the magnetic field that allow us to create the image, okay? So there's 3 coils, and we'll talk about the importance of each coil today. And then over the coming weeks, we're going to go into more detail of what each of those systems does, all right? So anyways, this is a very common design, not the only design. So in some sense, it looks like a CT machine. It just tends to be bigger. Essentially, you have a patient table. You put the patient in, you get them into the center of the bore, and then you start your imaging, okay? And that's basically what, you know, if you go to a hospital or an imaging center, most MRI machines will look like this. But we'll show you some examples of other designs that are out there as well. Okay. So we'll first talk about the main coil, the magnet coil, because that tends to be the biggest expense and also the heaviest component. Today, they're all made of superconducting wire. Okay, so this niobium titanium embedded in a copper core. And so essentially, you have to have a lot of current to create large magnetic fields. Okay, so if you go back to your E&M, basically currents are what create magnetic fields. And you need a lot of current because, as you'll see, we have very, very high magnetic fields in these systems. And so you want something that's superconducting so you're not wasting your energy in resistance, okay? So typically, I would say most systems out there use what are called low temperature superconductors, right? So you need this liquid helium to get things below 4 degrees Kelvin. But as we'll see later in this talk, there are some companies now that are looking at high temperature superconductors, which allow you to get some savings in cooling and weight, okay? The interesting thing about MRI is, you know, there are periods where it seems like nothing is happening, nothing is new, and there are periods where like people are inventing things left and right. We're in that period now. There's just a variety of things being invented. Hopefully one of you can be part of, you know, the next generation of new MRI systems. Okay, so let's talk. We're going to talk about magnetic fields. We need to get on base on terms of everyone on the same page about units. Okay, so the typical unit for describing the main field is Tesla. Okay, named after Nikola Tesla, not after the car. Okay, so basically Nikola Tesla was this amazing inventor in the early 1900s and did a lot of amazing things with electromagnetic fields. So we typically use Tesla. So if you go into a clinical imaging center, typically you're going to see a 1.5 Tesla or a 3 Tesla system. Okay. There are other fields you might see, but those are the most common. For example, here at UCSD in the hospitals, I believe we have probably 5 or 6 3 Tesla machines and maybe 1 or 2 1.5 Tesla machines. Okay. Now the other unit we use is Gauss. So it's unfortunate that sort of there's SI units and CGS units, and they're sort of both, especially in the US, we tend to use Gauss. In Europe, they stick with Tesla or millitesla. So the conversion is 1 Tesla equals 10,000 Gauss, okay? So, and then just for a frame of reference, a good thing to keep in mind, and as part of your upcoming homework, you'll actually get to measure this. The Earth's field is about 0.5 Gauss, okay? So that's a good number to keep in mind. And that's 50 microtesla, all right? So you can see that if I have so 1 Tesla is already, 20,000 times the Earth's field, okay? So 1.5 Tesla is 30,000 times the Earth's magnetic field. And then 3 Tesla would be 60,000 times the Earth's magnetic field. So as we'll see, these are incredibly powerful magnets, much stronger than the magnets on your refrigerator or anything you've ever experienced, all right? This is just showing that the field around here in San Diego is around 50 microtesla. So we are actually sort of at this area, and then the field increases and decreases in different parts. And as you know, the magnetic field is always changing, and at some point it's going to flip north and south in the Earth, okay? Okay, so let's talk a little bit about field strength. So here at UCSD, this is it from our imaging center. We have a bunch of 3T scanners. This is sort of like the sweet spot now for clinical imaging. There's probably thousands, if not tens of thousands of these across the world. I think I have a slide later that shows that. 7 Teslas are the next frontier that has just been FDA approved in the last few years. there's probably about 100 of these, maybe 200, approaching 200 across the world. So this is largely from Siemens. And then on the research side, people keep building bigger and bigger magnets. So this is a 9.4 Tesla at Chicago, a 10.5 Tesla at Minnesota, 11.7 Tesla at NIH, and 11.7 Tesla at Neurospin. Okay. So this 11.7 Tesla would be almost like 200,000 times the Earth's magnetic field. So it's a huge magnet. And let's see, what does this say? So yeah, so basically this just tells you in 2001, there were only 103 Teslas. In, I don't think it, 850 in 2015. And so probably we're over 1,000 now. And 7 Tesla in 2019, there are about 100 systems across the world. There are projects now, as we'll talk about, to develop 14 Tesla machines. So that's just like crazy, crazy strong fields. 11.7 Tesla, like these are huge magnets. See, this is a person and this is the magnet. Okay. So these are like, this was like a 20-year project. Okay. That employed a lot of French physicists. So basically, and unfortunately, they powered it up in 2021 and got this image of a pumpkin and some images of a excised brain, but they've been having so many problems getting this to work that this is as far as they've gotten after 20 years, which is not too good, but it's keeping a lot of people employed. Okay. This is what the magnet looks like. And so, for example, here, this is the main magnet here. Okay, that's what creates the magnetic field. Inside, you see this RF antenna. That's the radio frequency coil we talked about. And you'll also see it talks about these shielding coils we'll talk about. You see these additional coils on the outside of the main coil, and we'll talk about why you need those later. And then there's a lot of room for the helium to cool down the magnet. And there's a lot of cryogenics to sort of manage this cooling. And so the main thing is just the cooling of the magnet is a big part of the expense. Okay. And the stored energy is huge. It's like 338 megajoules, which I think a megajoule, I don't remember. It's something like, you know, taking like a ton of weight and accelerating it like 300 miles an hour or something. So it's like crazy amounts of energy. Okay. This is just showing sort of these field strengths from 10.5 to 14 Tesla. I just want to point out the weight. So 110 tons, 132 tons, 60 tons. And then this one we'll talk about later. It's only 15 tons. But these are like huge, huge, huge things. Okay. This is the magnet at, this is our old magnet here, one of our older magnets here. And what you see here is something you only want to see when you're replacing a magnet, which is helium, like leaving the magnet. Okay, so basically, when we replace a magnet, we have to power it down, and so that means removing the liquid helium, and then the current sort of dies away because of the residual resistance once it's no longer superconducting. But this is, you have to control this process very carefully. Helium will expand, and if, for example, if I opened helium in this room and we kept all the doors closed, we'd all be dead pretty soon. Okay, because you'd all be breathing helium. And so one question, so here's the first MRI question for you all. If you wanted to survive, what should you do? Assuming the doors were locked, and but the doors would open in like 2 minutes. So how would you survive in those 2 minutes? What should you do? Go to the floor. Yeah. So that's the only way. That's your only chance of surviving, because everything else would be helium. Okay. And in fact, unfortunately, typically, I think once every few years, someone will die because of this. Typically, one of the people, engineers installing this, there'll be a leak and they don't know it. And by the time they know it, they're suffocating and they pass out. Okay. So anyways, just part of my job today is to scare you, because these are very dangerous machines. And so I do want, if nothing else, you need, and we'll show you later, you do need to respect that there's a lot of stuff going on. Okay. Typically, these are big things. So we have to rent these huge cranes to put in the magnet. And then this is what the side of the magnet looks like. So a lot of the electronics is right outside the main magnet. And this is them pumping liquid helium in. So typically, the way these are shipped is they have maybe some helium in them, but you have to put more helium into them. And then you basically plug it into the wall. You start charging it up. And once it's charged up to field, you unplug it. Okay. And that's it. You don't leave it plugged in, at least for this design. So this is our current Siemens magnet that we have here at the fMRI Center. Okay. So let's talk a little bit about what can go wrong. So these are basically, if you bring anything steel or magnetic into the MRI room, it will be sucked in. Okay. And so this, unfortunately, this person is trapped there. I'm not sure if he lived or not. I haven't updated this since last year, but there was in 2021, a 6-year-old man was killed by an oxygen cylinder. This tends to be the most common cause of death. For whatever reason, people just forget and they bring in oxygen cylinders, which are steel cylinders, and they go flying into the magnet. And generally, whoever's in the magnet will then be immediately killed. Okay. I'm not going to play this video for you, but you can go to YouTube and watch it. I highly recommend watching this. It's a fun video to watch. You'll see lots of interesting experiments and just hopefully convince you that none of you here, like if I gave each of you a steel wrench and said, approach the magnet and said, hang on, no matter what, as you approach the magnet, none of you here is strong enough to hold on to that wrench. Okay. It is so powerful. It will be literally ripped out of your hands. Okay. I don't see anyone here who I think, unless we had like the Hulk or something, and even then, I'm not sure he could hold on to it. The other thing you need to know, since most of you will probably have an MRI exam sometime in your life, is the magnet's always on. Okay. Now, as we'll talk about later, sometimes the magnet makes a lot of sound when it's actually scanning. It's actually quite a noisy process. But even when it's not making any sound, the magnet's always on. Unless you're told explicitly that it's off, you should assume it's always on. So even if there's no sound coming from the magnet, it's always on. So never go into the magnet room thinking that the magnet is off. Now, the worst thing that happened obviously is an accident. But then even if you're not in an accident, the annoying thing is if you go in, all your credit cards will be wiped out too. So that's no fun either. So, and your iPhone might be screwed up as well. So just, the magnet field will screw up a lot of things. I think even, I've been in the magnet probably over 100 times. And I think the only advice I would give you as someone who's been in the magnet a lot is even if you're in there for a clinical exam, it is your life. So they generally give you a mirror and have not asked for a mirror so you can see people at what they're doing and just keep an eye on them. And if you see anyone walking in with an oxygen cylinder, just yell, So I'm very paranoid, because I know how strong it is. So just a word of advice, if you learn nothing from this course, the magnet is always on and take care of your own life. Okay. But it's perfect. It's generally safe. I mean, no patient, mostly it's very rare. It's like maybe one death every few years, which is already too much, but it's a relatively safe modality as long as people understand that you should not bring metal things into the magnet room. Okay. Okay, so let's do our first sort of exercise of this lecture in terms of I'll use the poll. And so what we're going to do is I'm going to launch a poll for Zoom. So if you're on Zoom, you can respond to the poll. If you're in class, what I find works best is just when I say 1, 2, 3, you're all going to yell out your answer. Okay. That we'll just do an audio poll. All right. That sort of saves time. So here's the thought experiment. You've walked into the magnet room. You've totally ignored what we just talked about. And you've brought in a big metal object. Okay. And at some point, it's going to be ripped out of your hands. Okay. So you're at point A. So the question is, let's say it's going to go flying into the magnet, right? We've told you it's going to be pulling the magnet. So how far is it going to go into the magnet? Or at what point is it going to stop? Okay, so you have choice of A, B, C, D, or E. I'm going to launch the poll here. So let's see, end that poll. Whoops. I'm going to relaunch this poll for some reason. Let's see, relaunch. Okay, so it's arbitrary multiple choice online. You can choose A, B, C, D, or E. we'll give it, and for this part of the course, feel free to talk to your neighbors, discuss it, and we'll give you about a minute to discuss this with your neighbor, and then we're gonna do an audio poll. All right. So where do you think this metal object is going to end up? Oh, just wait for a minute. Yeah. Yeah, feel free to talk, discuss. Yes.
When we went to take MRI scans with our joke, something happened at the MRI building. I never understood the shimmy kind of squares.
Yeah.
Like the shimmy concept, I don't understand.
We'll talk about
I
that.
don't know if we're talking about.
Yeah, I can mention it.
Like, I'm keeping an eye, like,
Yeah.
I know you knew, and I was like, this.
Yeah. Yeah, we can talk about that. Yeah. Yeah. We'll talk about it when we get to gradients. Okay. Okay, so we have pretty good participation online. So before I tell you what the online results are, let's in class at the count of 3, just yell out your where you think it's gonna stop. 1, 2, 3. Okay, so unanimously C. Online, B was 44%, C was 50%, and D was 6%. Okay. Actually, it's gonna go to E. Okay. Right, because think about potential energy. It's got a bunch of potential energy here, and it's sort of like if you have a ball, right, and you let go, it's going to go all the way to the other side of the the parabola, right? So yes. Yeah, assume as in a physics class, assume an ideal object, assume it's going to go straight through. Okay, ideally, yes. It could go in any way and hit the walls, but we're just going to assume an infinite, like just assume an ideal condition. Okay. So just as if when we do physics problems, we have a ball rolling up and down, we don't worry about, other things. Okay. We just assume an ideal ball rolling up and down. So this would actually go to here. Okay. So that's where it's going to stop. So then the next question, which I'm going to give you another minute to think about, is where is it going to go next? Okay, so go ahead and take another 30, 40 seconds and discuss this and think about where is this going to go next? So it's at E. Assume ideal conditions, right? Ideal objects. Okay, so in class at the count of 3, 1, 2, 3. A. Yes, right, good. So it goes back right at you. Okay, and so I think A was the most popular answer online as well. So that's right. So that's another part of now obviously if there was a person in the magnet, it would hit them first. So all bets would be off. But if you walk into a room with an empty magnet, you're the most likely person to get hurt. And I've met people and I've met someone who almost lost a finger because of this, very experienced engineer. I've heard of people getting really hurt from this. Your only hope is that it doesn't go in a straight line and it hits the walls and causes lots of damage before it comes back. It slows it down. But if it goes straight through and back, which it can, like if you're right at the center and it gets pulled out right in the center of the bore, it will just go boom, boom before you, so fast that, the moment you feel it's being ripped out of your hand, it will have already hit you. Okay. So just, this first half hour, I'm just scaring you. Okay. All right. Any questions on that? Okay.
would it go past you? Is it getting ejected from the cylinder, or is it going to oscillate?
It's going to oscillate. In the ideal world, the only thing that's going to cause it is gravity bringing it down. But this is so strong that it's way stronger than the force of gravity, right? Yeah, gravity doesn't rip your wrench out of your hand, right? Okay. All right, good. Any questions? Okay. So one of the things we have to do, sort of a safety point of view, is there is a very strong magnetic field. And because for safety issues, we don't want that. Let's say we put a magnet in this room. We don't necessarily want the magnetic fields to go out into the hallway. So if someone's just walking by, that they're exposed to the magnetic field. So we put these sort of counterwinding that have current going the other way to create sort of an opposing magnetic field, such that the magnetic field inside is not really affected, but the magnetic field outside is reduced. Okay, so that's what's called reducing the fringe fields. So this is what the fringe fields look like on a magnet. So essentially, the fields are very strong, close to the magnet. So here at the isocenter, it's 30,000 Gauss. Okay, that's for a 3 Tesla system. And typically, we need to get it down to 5 Gauss. That's sort of the requirement, the safety requirement, I believe from the FDA, that basically the 5 Gauss line needs to be confined within the magnet room. Okay. So we actually ran into an issue with this when we were sighting a magnet, because we were replacing one magnet with another magnet. And if we put it in exactly the same place, then this 5 Gauss line here would have extended into this public walkway, which was like an emergency exit walkway for people. So what would be the problem if someone was like, if you were running here and you went through this 5 Gauss line, what sort of person do you think would be most at risk? Like, why do we even care about people walking through in a magnetic field? Any ideas? If they have implants, especially, and I think that the requirements are probably too stringent, but the fear is always that, remember from Maxwell's equations, if you time varying magnetic fields cause electrical fields, right? dB/dt, right? So one way you can create a dB/dt is you can run through a field, right? And that's a dB/dt. So that's going to cause electrical current. And the concern has always been, especially if you have a pacemaker or something, is that going to screw up the pacemaker? Okay, so that's why we're still very conservative. Quite frankly, it's probably not an issue. You'd have to like be running right next to the wall and running really fast, but still, we had to. It's not our job to come up with the regulations, so we have to follow the regulations. So then, in this case, we actually had to move we just moved the magnet 27 inches away from the wall. Then now that field is well confined within the wall, and the public walkway is clear. So that's, when you're sighting these magnets, there's just a lot of things you need to think about. Okay. Let's talk a little bit about different field strengths. And so we showed you, this is sort of the most common design, but there are other designs. For example, in San Diego, there is this upright magnet that you can go to, I think near Hillcrest, okay, which has basically 2 coils, 2 sort of magnets that are creating magnetic field between them, sort of a pancake design, and also this sort of design here. These tend to be lower field magnets, like 0.3 Tesla or 5.05 Tesla. So why might you want a design like this? What's the advantage of having this sort of design? Any thoughts? So what's the advantage of having this design versus this design in terms of the subject comfort and safety? Like if you're an engineer, so you're all engineers in here, presumably, or physicists. So your boss comes to you and says, I need to design something like this. Like, why would you, after saying why, your question is, why do I need to do that? Or why would I have a design like this? So as an engineer, what do you see as advantage of these designs? Yes.
Less stressful for the patient. The patient's probably less likely to move. So that's gonna, when they're feeling more comfortable, and so that will basically decrease the amount of time that it takes to burn the ride.
Yeah, it's really a lot of it's patient comfort. Some people do get fairly claustrophobic in these magnets, right? And so if you don't need the high field strength, then this is going to be better. This one's also good because you can actually image them standing up. You can look at their back motion, and so there are there's a group at UCSD in orthopedic surgery that's using this magnet to look at sort of lumbar pain and look at the spine as people are in different flexion. Okay. So just to say that even though this is the most popular design, that's not the only design. Okay. The other thing that is happening is there is a helium shortage in the world. Okay. So much so that I think a few years ago you couldn't buy these balloons, right? Helium balloons for birthdays and things. And so MRIs, most MRI systems use a lot of helium, and helium. There used to be a place, I think, in Oak Ridge that generated helium and was mandated to do that, but then the law sort of expired and they weren't creating any more helium. So how much helium is going to be produced is sort of something that every few years there's sort of a bit of a concern about that. Okay, so that's sort of leading. Also, helium is really expensive. Okay, the last time we had to if you have a magnet, you'll typically have to pay the vendor at least, to maintain a magnet is anywhere from $100,000 to $200,000 a year. Okay, and a lot of that is they're trying to cover the cost of helium. If they really have to fill up the helium and pay for all that helium, it might be $100,000 for a helium fill up, or on the order of hundreds of thousands of dollars. Okay, so it's not cheap, and so typically the magnets are designed such that they recover mostly as the helium evaporates, they recondense it, and so it's a closed system. But if you do have a helium leak and so we monitor the helium levels very closely, and if we see them going down, then we call the vendor immediately to get that taken care of. So that's led to so here's a classic magnet technology that uses about 1,500 liters of liquid helium, and now people are realizing with really advanced refrigeration techniques and sort of ways of pulling heat out more directly. This one actually, a 1.5 Tesla machine only uses 7 liters of helium, and this 0.5 Tesla uses only 0.7 liters of liquid helium. Okay, so not only is it cheaper, but it also makes it much easier to sight because it doesn't weigh as much. Okay, and also from a safety point of view, all magnets with a lot of liquid helium, you have to understand if there is ever a catastrophic failure, then that helium will want to go out into the environment. So you have to create all these pipes to let the helium vent out. So you have less helium, then you don't have to have this expensive an installation. Okay. Okay, so this is that 0.55 Tesla system. And so there's sort of in medicine, there's always these different trends. So one trend is to make magnets bigger. Okay. From a clinical point of view, it offers more room, and also in certain areas of the world, people are just getting bigger. Okay, and so there's a trend to making magnets bigger, both for patient comfort, but also sometimes if you want to do a procedure or something, it gives you more room. On the other hand, there is a trend towards making lighter and more portable magnets. Okay, so this is I think just got approved. This is I think it's a 1.5 Tesla magnet for neonates, for babies. And this it uses one of the first, I believe this is probably one of the first commercial systems to use high temperature superconducting wire. Okay. And that allows them to get away with no liquid helium, I believe, right? And that basically, that allows them to sight it. Like we could put one in this room very easily. All right. And in fact, the Netherlands the Dutch Science Institute has just announced a plan to build the 14 Tesla system, which would be the first in its world. And see, a typical low temperature superconductor, you have to operate at 4 Kelvin. They believe that the maximum that they could operate is 20 Kelvin. Okay. And they're going to try to, when I look at the specs on it, they're going to try to operate this around 8 Kelvin, just so they're not right at the limit of what the wire can withstand. So the advantage is that you can sort of see it allows them to have a lot much smaller magnet. They don't need liquid helium, and plus the high temperature superconductor can carry more current per unit cross section, and so you can actually use less wire and have a much lighter magnet. This is the same company that built that neonate magnet, and you can sort of see it's much less heavy. This was whatever that is, 60 tons, and this is 12 tons or something like that. Okay, so this is just brand new. So you're already seeing, so probably over the next decade or so, we may, if this is successful, we're probably going to see more high temperature superconducting magnets. This is where they're going to site it on a lawn outside a building. Okay. The other trend is to go to really, really low fields. And so this is an FDA approved magnet by a company called Hyperfine. This is a 64 millitesla magnet. Okay. So basically, this is, 1,000 times, roughly 500 times less than a 3 Tesla field, right? And only about 1,000 times stronger than the Earth's magnetic field. Okay. So this is nice because this actually, you could just wheel it down the hallway. We could just plug it in. We could start scanning you like in minutes. In fact, this is me being scanned earlier this year in Toronto at the annual MRI conference, where they just had a booth and you could just sign up and get scanned. And one of my former postdocs works for the company now. So I said, oh yeah, let's, can you scan me? And they're, got in line. And so this is him. As I'm being scanned, it's being sent to an iPad, the images. Okay, so these are actually the images from my brain in a 64 millitesla machine. And they're actually quite good, okay, for something that, and this is using, the magnet design is, you can sort of see the magnetic field is going this way. So it's not a circle, it's the magnet, there's 2 permanent magnets and it's creating magnetic field this way, okay. And so as we'll talk about sort of towards the end of the course, a lot of this, the reason why these images look as good as they do at this low field strength is because of deep learning, okay. They're really taking advantage of AI to make these images look a lot better, okay. Traditionally, these images, if you just use traditional recon that we're going to talk about, these will not look as good. And we'll get to that sort of at the end of the course. So the way the course trajectory is, you're going to learn sort of the conventional way of doing MRI, which is still how it's mostly done. But because we're in this revolutionary period of deep learning, we're also going to have to touch upon, what it's going to look like. It's already changing now, but it's going to become the way you have to understand imaging moving forward. Okay, any questions before we move on? Okay, so we've talked a lot about this main field here. So the main field is and this main field is the main magnetic field. We typically call it the B0 field. Okay, so B0 stands for the main field. Showing up okay? All right. The next thing we're going to talk about is this RF field, which we call the B1 field. Okay, and the job today, we're just going to touch upon sort of what it does, and then we'll get into more detail later. In every magnet, there's typically what's called a body coil. At least most conventional magnets, a body coil, which can transmit and receive on its own. But in addition to that main coil, you can also have localized coils. So this is a localized RF coil here, which is a knee coil. So you can put it around the knee and that would transmit and receive. So T and R means transmit, receive. Okay. And in addition, you can have, so this is transmit, and receive. In addition, you can have these coils here, which are receive only. Okay, so you can have the body coil will do the transmitting, and then you can have localized coil that do the receiving. So this RF can either be done with the same coil or 2 different coils. All right. So this is an example of what a main, so this is once again the B1 field, B0 field, and this is what a body coil looks like. Okay, so that's typically most of, if it has a cylindrical design, the magnet will typically have at least a body coil. All right. But as we said before, there are, especially over the last, say, 20 years, there's been a trend of lots and lots of receive coils. So 20 years ago, if you wanted to buy a magnetic MRI system, it would typically only come with 1 channel of receive. Okay. Today, if you go out and buy an MRI system, so for example, our systems here at UCSD have 128 channels of receive. Okay. And so there's been a revolution over the last 20 years of getting much more information. Okay. And so now typically you have many, many coils surrounding, and each of these coils is a receive only coil. So this coil does the transmit, it perturbs the spins, and then all these coils are listening in, okay? And as we'll get to later in the course, the fact that you have so many coils, that becomes a big part of, why you can do reconstruction faster, better, and then take better advantage of like deep learning and other algorithms. These are some, I think, these are just all homemade coils, showing you sort of, literally these coils are essentially loops of copper wire, typically with some filtering and preamplification. This is sort of, I think, from Siemens. Like this is a array coil that fits over the whole body, and there's just lots of little coils all throughout this array. Okay, and they're each sort of looking at just a certain part of your body. This is these are both 32-channel coils. What you can't see in these look really nice, but if you open the hood, this was the prototype of this coil. So this was a coil built at Harvard MGH, and you can sort of see it's sort of like a soccer ball design, just these overlapping wires. And then after a lot of engineering, they made it a little more practical. Okay. Okay, so that's for today. So we'll get back to RF coils in a bit. The last set of coils we're going to talk about are MRI gradients. Okay, and these are to generate magnetic field variations. Okay, so the general picture you want to have in mind is you pay a lot of money to have this big field, the B0 field. Okay, and ideally you want that to be very uniform. Okay. And so there's a process of shimming where actually when they install the magnet, make the magnet, they put in little iron. The magnet is not perfectly uniform, so you can add little iron here and there. And there's an art to sort of adding just the right amount of iron such that the field is fairly uniform in its sort of a volume of about this big. Okay, so big enough for most bodies. You have a uniform field. And then what you do is you come in and you actually add on very well controlled, and typically in this class we'll talk about linear gradients. Okay, we'll talk about what that means. And so for the gradient coils, you'll typically see an X coil, a Y coil, and a Z coil. And these creates gradients in the X, Y, and Z directions. They have these really funky patterns to them. This is, I think, a guy at the Siemens factory sort of finalizing the construction of a gradient coil. And so what do we mean by gradients? Okay, so basically at every location, and for now, we're going to just focus on the Z component of the field. So the B0, the main Z component is this B0 field. Okay, that's the main field that you always have. And Z is sort of the direction along that main field. Okay. And then what we do is we add on a dBz dx term multiplied by X plus a dBz dy term multiplied by Y. And so these dB dx, dB, dy, dBz, dz, those are what we call the gradient fields. So the overall field is just the main field plus the gradient times this X, Y, and Z. And these gradient fields are then what allows us, we'll see later, to create sensitivity to different locations in X, Y, and Z. And that's what allows us to do the imaging. If we just had the B0 field, you could make an image, and I might talk about new ways of doing that, but it's only, for most MRI systems, it's only the fact that you have these gradient coils that allows you to make an image. Okay, so let's look at what one of these coils looks like. So this is the Y direction, this is the Z direction. If I have dBz dz greater than 0, that just means as I move along the Z direction, the field is getting stronger. So this would be a positive GZ gradient. Okay, and then if I have a GY gradient, it means as I move along the Y direction, that BZ field is getting stronger along the Y direction. So that's what a gradient field means. Okay. The simplest designs are, and this actually, let me just get a shout out, especially if you have questions or even for your project, this is always a good place to go, MRIquestions.com. It's like this retired radiologist who just spends all his time like keeping this website alive. It's amazingly useful. It's got lots of answers to all your MRI questions. Okay. So he actually shows, for example, if I just want to make a Z gradient, the simplest design is I have current going this way in one coil and current going this way in another coil, such that in between, this wants to create a field going this way, this wants to create a field going this way, such that in between, I get this linear gradient in the field strength. Okay. Now, actually, so this is the simplest thing you could do. In reality, you have to have many more coils, and there's a whole art to designing it. Okay. And as you can sort of see here, the simplest way I could get a Y gradient is have this these sort of what's called Golay coils. This would be the simplest design, but as you can see in practice, you have these really funky designs that are essentially computer generated. So basically, they have an algorithm that just sort of does a search and generates these coils that create the best gradient you can have. Okay. So the gradients are typically what makes the most sound in an MRI system. And so essentially we run a lot of current through these gradients, okay? And to do that, we have these huge gradient, well, they're not as big anymore, but they're very powerful gradient amplifiers. And so, for example, you might have, 1,000 volts, 1,000 amps of amplification. So that's like a 1 megawatt gradient amplifier, right? And just to tell you 1 megawatt, this means that you could take one of these amplifiers and take it to a stadium and you could have a rock concert, right? So for example, I think when I looked this up, the Metallica World Tour, does anyone here know who Metallica is? Okay, so some people know. So there it was like only 367 watts for the sound for that stadium. So basically what happens is we pump a lot of current into these, and because we're switching these, we're going to find out that these are actually the B0 coil. The main magnetic field is always sort of on and steady. The RF coil we'll see, we pulse on and off, and the gradients we also pulse on and off. So there are, of the 3 coils, 2 have time varying signals on them. And that's what makes MR very cool, because you can play those any way you want. Okay. And that leads to thousands, tens of thousands of ways you can do MRI. All right. So that these are the coils that do that. And then once you have all these coils, then, for example, you've got the main magnet. Okay, so Mary Lou's asked a question about shimming. And so there's a shim power supply. And so one thing is that, even though you want a sort of a uniform magnetic field, but as we'll see later, whenever you put an object in or there's non-idealities, there's a perturbation in the field, okay? So you can use these additional coils to create additional fields to sort of counteract that. And you're trying to make the field as uniform as possible in the area that you care about, okay? So that's what the shimming is for. These control the gradients. Here's the RF chain. And then there's a lot of electronics, data storage, computers. And in the old days, this would take up a lot of room. But nowadays, you can actually go and just this is an article you can look up. There's a lot of companies that are essentially, you can just have this running on a PC now. Okay. So I think we are in the age where there's sort of 2 trends. One is very huge magnets and we'll talk about why you would want to make the magnet really big. And then the other trend is more portable magnets, lighter, low cost. Okay. And so I think there's room for both. Certainly in the startup area, it's better to go to the low cost one, because these magnets the other ones cost tens of millions of dollars and require a lot of engineering. Okay, so before we start delving a little deeper, are there any questions? Okay, if there's no questions, we're going to now get into sort of the talking about what each magnet does and give you a little more insight. So there are the main magnet, its job is what's called polarization. Okay, polarization means creating some magnetization that we can work with. Okay, the RF coils have 2 jobs. One job is excitation, take that magnetization and perturb it. Okay, the gradient coils do what's called encoding. Okay, they basically get the magnetization to do things differently depending on where you are in space. And that's how we started encoding the image. And then the last step is integration. The RF coil sees the signal from all the magnetization within its field of view or within its active area, and it essentially integrates it. Okay, so there's really 4 main steps that we need to go over to understand how MRI works. So, and then the cool thing is that with that, these are just 5 examples of what you can do with the same MRI system. And I could have shown you hundreds of examples, okay? And so as compared to a lot of other modalities, MRI is super, super flexible. And over the years, people have come up with new ways of using MRI, and new ways are being invented every year, okay? So you can certainly use MRI for getting, and so the most prevalent use of MRI is to get just, what's in the brain or what's in the object. And so here, these are 3 images of the same brain, okay? And and we'll see how we do this later, but just by tuning the parameters in software, these were all acquired, this is maybe 5 minutes, 5 minutes, 5 minutes. You can actually highlight different tissue areas and make some areas look darker or brighter just by changing the timing and of your sequence, okay? So that's sort of, if you go in for a clinical exam, you'll typically have one of these exams done, okay? But you can also use MRI to sort of figure out where all the blood is in your brain or in your heart, okay? Or where the veins are, okay? So this is looking at iron in the veins. Or you can use MRI to figure out what's the wiring of your brain, okay? So this is actually, I find this still incredible. We can take any of you and put you in the scanner, even for 8 minutes. Longer would be better, but even for 8 minutes, and we would essentially have a wiring diagram of your brain, okay? There's no other way you can do this, right? I mean, before MRI could do this, you could only do this in like, animals that you could kill, right? Or inject agents into them, and you can maybe track one fiber at a time and see where that agent went, or you could chop up their brain and slice it into like thin slices and try to track it. But as far as I know, this is the only way to do it in vivo, okay, where the subject survives the exam. All right. So this is all done with MRI. We'll talk about this towards the end of the course. This is what's called diffusion tensor imaging. And then one thing I work on is functional MRI, which is actually seeing what your brain's doing functionally. Okay. So these are just 5 examples. We'll probably touch upon all of them. Yeah, we'll touch upon all these examples later on in the course, but there are many, many other things you could do with MRI. Okay. So the MRI portion, just because I do brain, will be brain-centric a little more versus the CT was more cardiac-centric. So at least you're getting both organs in the same course. All right. Okay, so we're going to now start getting into the nitty-gritty. And the first thing we're going to cover is polarization. But to do that, we need to talk about spin. Okay, so this is not a physics course, so we're not going to go into what is spin really, but I think most of you've heard of it. It is essentially, you can think of it as the intrinsic angular momentum of all elementary particles, electrons, protons, neutrons. Okay, it's a key concept in quantum mechanics. There were some very basic experiments done in the 30s showing that spin exists and it's quantized. Okay, so it is a very key concept in quantum mechanics. We're not going to use any quantum mechanics in this course. We're just going to sort of take a classical view of what's going on. Essentially, it's good enough for engineering. Okay. But it is useful to think about what it means to have. So if I gave you a ball and I charged it up, right, and I spun that ball around, right, that's essentially like charge moving around, right? So that's a current, right? So I'm creating it. If I take a charge here and just spin it around its own axis, it's going to create a current, and that current's going to give a magnetic field. Okay. So the thing about spins is they have both angular momentum and a magnetic moment. And so those two things become very important. Okay. Now, remember, this is just a classical analogy. This is not really, this is not how you would describe a spin, but it's a useful analogy. And so the magnetic moment is related to gamma. This is something we'll see a lot, the diagram ratio times the spin angular momentum. Okay. And typically in this class, we're going to focus exclusively on the hydrogen proton, simply because there's, most of your body is hydrogen. And so most medical imaging is based on hydrogen proton. Now, there is imaging, like people will look at like sodium or phosphorus. And obviously you can inject, 13 carbon or 19 fluorine. So some of these are existing naturally, but others you would have to inject in. but these are in such low concentrations that it's really, really hard to do the imaging. People are doing it, and there are some examples where people are trying to push this forward, but it's just these tend to be very low SNR methods, whereas this is a very high SNR measurement. Okay, so if we thought about a current going around a loop of wire with area, cross-sectional area A, then this would have a magnetic moment of mu equals I, the current, times the cross-sectional area, times n hat. N hat is just the direction vector. Okay. And so the first thing we want to think about is what happens if I have a magnetic field and I put this loop in that magnetic field. Okay. And the one thing we want to think about is where is the energy going to be the lowest and the strongest. Okay. And it turns out if you go back and look at the Lorentz forces, it turns out the minimum energy state is when the current is in this orientation such that this moment is aligned with the field. Okay, so that's one thing to keep in mind. The lowest energy state is when the magnet moment is aligned, and then it would take me energy, or I have to do work to go like this, right? To flip it the other way. So this would be the maximum energy state. I've had to put work into the system to get it to that state. Okay. And then in between, there's all these other energies that you can have. All right. So just know that there's a minimum energy state, maximum energy state, and lots of energy states in between, depending on the orientation of that magnetic moment. All right. So I mean, we see this all the time. I forgot to bring my compass, but you can imagine, if you have a compass needle, it's going to point. It's going to be in its lowest energy state, right? That's pointing. It's when it's pointing north, and then to move it to a point south, you've got to put work into it, right? And it's just going to try to go back to its equilibrium state. Okay. So what that means is that if I just had a collection of magnetic moments at different orientations, and I asked, how much of what I see of any given orientation, what you're going to find is it follows what's called the Boltzmann distribution, which you've probably seen in some of your other courses. And so I have the highest probability of finding spins in the lowest energy state. And as I go to the high energy state, the probability of finding spins falls off exponentially. All right. This is an example I heard when I was in grad school, which I still think is a great example, which is it's sort of like, if you go to the Gilman parking structure, any parking structure on campus, and assume there's no like A, B, or S, things, you could park anywhere you want. If you come in the middle of the day, the first thing in the morning, you're just going to park on the lowest level, right? Most people will just park at the lowest energy level, right? Few people will want to go all the way to the top just because they want to be at the top. But you would find a roughly exponential distribution of maybe the person had a lot of coffee, so he just wants to drive more. Okay, so you will find a distribution of people at different levels, but you will tend to find more people at the lower levels, low energy states, and less at the higher energy states. Okay, so that's one way you can think about what the Boltzmann distribution is trying to tell you. Okay, so then we have this picture of if there's no magnetic field, right, then there's no preferred orientation, right? So the spins, you would imagine magnetic moments pointing in every given direction. So if I took the vector sum of lots of vectors pointing in different directions, and I put all their origins at the origin, the tails of those arrows at the origin, they would all sum up to 0, right? You've got all these vectors pointing out, and the sum is just 0, okay? But now, once I create this magnetic field, now there's a preferred orientation. So even though they're still randomly distributed, there's going to be enough of a bias towards this such that there's going to be a net magnetization. That's the polarization that we're talking about. Okay, that's the net magnetization we're trying to create. Okay, so even right now, sitting here in this 50 microtesla Earth's magnetic field, you are slightly polarized. Not very much, but there is a tendency of your spins to be, I don't know which way the magnetic field is pointing here, but it would be pointing in that direction. Okay, so that M0, and so M0 is typically what we use to call that equilibrium magnetization that the B0 field creates. You'll see it's related to the number of spins you have in your body. So essentially for hydrogen, that's how many hydrogen protons you have per unit volume times this B field, okay? And so this is why people keep building bigger and bigger scanners, because the bigger B field you have, the more of this polar magnetization you create, and that creates your signal, okay? And that's why you can sort of see, if you look at signal noise ratio, it essentially scales almost linearly with magnetic field, okay? And so that's why people are willing to spend tens of millions of dollars to get more signal noise ratio. Okay, so in CT, you would turn up the voltage, right? Or you know, you can crank things up, or the current, actually crank up the current. In MR, you've got to build a bigger magnet, or come up with better ways of processing your data, like deep learning. So if you operate in this regime here, where you have low SNR, you better find a good way of getting rid of the noise. Okay. Now, those same games can be played up here. So you can even get further gains, but in general, the physics tells you the bigger field gets you more signal. The problem is that at bigger fields, as we'll find out later, the frequency of the fields also increases, and that creates problems with, you have to start really doing very intricate electromagnetic analyses. Okay, we'll talk about that maybe later. Okay, so for today, let's just really focus on sort of what happened. So basically, if I have a, so imagine this, like this represents a spin, okay? So if this is a magnetic moment and I have a B field like this, then it will tend to be aligned with this field, right? And if I somehow perturb it like this, it would just try to go back. Okay, so any perturbation of this would tend to go back, okay? But now I have to imagine, what if I have a rotating magnetic field here in the presence of this? And so that's what we want to look at, okay? So it's hard to do with this. So I have, every year I bring a light tire. I can do this without falling. Okay, so this is going to be our spin for today. Let me just make sure I'm on the video. Okay, so this is obviously the lowest energy state of this wheel, right? What's the force acting on this? Gravity, right? I mean, obviously there's a counterforce of me holding it up otherwise, but now, and what would be the highest energy state of this wheel? How could I put it in a higher energy state? Flip it over, right? Okay. And then where would it go? It'd go back here, right? Okay. And if I just perturb it this way, it would just go back there, right? So this perturbation is what the RF field does. So this sort of component here, it's sort of, imagine there's some polarization here. When I tip this away, that's putting energy into the system. So the job of the radio frequency field is to put energy in the system, so perturb it away from equilibrium. Okay. Now, if it didn't have any angular momentum, if I perturb it away, it would just come back. Okay. But the cool thing is it has angular momentum. So it precesses. And that's exactly what magnetic spins do. Okay, you perturb them and they precess. Okay, so that's the key insight you need to have. So there's going to be now a frequency of precession. You know, if this was a physics course, we would calculate how fast this is going around. Oh, it's getting tangled on itself too. Okay, but that's essentially what we're talking about. So if I have basically angular momentum and torque, so if it's not spinning, there's just going to be a torque applied to it. But if it's spinning, there's going to be precession, just like a gyroscope or toys you played with probably in the past. Okay. All right. So let's see, where are we? Okay, so that picture is just saying that if I have, this is just the equations for precession. We don't need to really go into them too much detail. The main key is that there's going to be a frequency of precession. Okay. And it turns out that frequency of precession is gamma times the field. And this is what's known as a Larmor frequency. Okay, so that's the first sort of important concept that we need to think about, which is that spins precess, and there's going to be a certain frequency precession. Okay. And our job is that means that there's preferred for every magnetic field, there's a preferred frequency of the spins. And that becomes very important in designing our system. We need to take that into account. Okay, let's talk a little bit about we already talked a little bit about units in terms of Tesla, 10,000 Gauss. Earth field's about half a Gauss, which is about 50 microtesla. Now we're going to talk about what the diagrammatic ratio is, and this is for hydrogen proton. Okay, so it turns out to be 26,752 radians per second per Gauss, which turns out to be the number I think about is in terms, instead of radians per second, I tend to think, engineers, we tend to think in terms of hertz, cycles per second, or megahertz, millions of cycles per second. So it's typically about 4,000 hertz per Gauss. Okay, so that means that right now, sitting in a half Gauss field, your spins are processing about 2,000 times per second. You don't feel anything, but that's what they're doing. Okay. And then the other, so for if you're in low field, then Gauss, hertz per Gauss is a useful thing. And so typically when we're talking about like the RF field, Gauss might be important. For the B0 field, when we're up in the Tesla range, then it's more useful to think about 42.58 megahertz per Tesla. Okay. So that means for a 3 Tesla system, I'm going to be at about 127 megahertz. That's the frequency I'm at. Okay. Yes, question.
Different location of the Earth or different planet?
Gamma is a constant for the proton itself, but in the localized environment of there can be things where like you don't find isolated protons. In water you find H2O, but like say you hook up a proton to a carbon atom, right? Or it's in a carbon chain, then there'll be that molecule itself will tend to have different resonances as well because there's different interactions. So that's, and if anyone here is a chemist, that's the basics of NMR spectroscopy, that different molecules will have different frequencies because their local electromagnetic environment is different. Okay. And then there can be different resonances due to bonds and things like that. But for this course, you can just assume gamma is a constant. Okay. There are other diagrammatic ratios, for example, for sodium and phosphorus. But as we talked about before, look at the abundance here, 88 molar versus millimolar concentrations. Okay, so the relative sensitivity is a factor of 10 or 10 or more for hydrogen proton. So just to give you a sense of what these frequencies are, so 1.5 Tesla system would transmit about 63 megahertz. 3 Tesla would be 127 megahertz. The local public radio station here in San Diego is 89.5 megahertz, right? So we're right in the FM band, okay? And in fact, for a 3 Tesla system, 127.8 is right in the civil aviation band, okay? So that means that MRI systems are operating at the same frequencies as a lot of other stuff in the world. And so that's why if we wanted to put an MRI system in this room, we'd have to cover this with copper shielding to sort of shield this room from all that electromagnetic interference. Otherwise, as we'll see, and you'll see in an upcoming homework, if you inject interference, different frequencies, then that can screw up your image. Okay, so for example, once in a while we have these doors that are shielded, and if you have, say, a crack in that, then some RF interference can get in, and you'll see that the image quality goes down because you're injecting energy that's just coming from some other source. Okay, so in MRI, we don't necessarily look at any one spin, right? We're always looking at a lot of spins together. So if you have a voxel, say 1 millimeter by 1 millimeter by 1 millimeter, there's lots and lots of spins in there. So typically, we're always looking at the net magnetization, which is just the sum of all these little magnetic moments in some volume. And it turns out that that magnetization follows this precession equation. So this is the equation of motion for magnetization. All that means is just that magnetization will precess around the field. Okay, so essentially the cross there is just the vector cross product, which some of you, it's been a while since you've seen that. So if I have m cross b, then it just creates a force perpendicular to that, and that creates this precession. Okay, so then the next thing, I think we have time. Yeah, let's talk about RF excitation. So we talked about how the B field creates this net magnetic moment, and then the job of RF excitation is to perturb that magnetization away from its equilibrium point, just like I did with the tire, okay? So it takes energy, this is its lowest energy state. So by putting energy into the system, I allow it to go to some other state, okay? So this is, let's see, is there a movie here? Yeah. So this is a spin processing around the B0 field. And then as I add energy into it, you see that that magnetic moment gets perturbed away from its equilibrium point, okay? And I can stop it at any point, but the more energy I put in, you sort of see it just keeps going away and away, okay? And at some point, it's going to perturb back, yeah, okay? So that's the basic picture we have in mind for perturbation. You have this net moment, and you put energy into the system, and it starts moving away. Now, as it's moving away, it's also processing, okay? So two things are happening at the same time. So how do we tip magnetization away? Well, we've talked about the B0 field. So the main field here runs against is the B0 field. Now we add this B1 field, okay? So the B0 field is typically here, and we add a B1 field perpendicular to the B0 field. And this is the magnetic field we add that will cause magnetization to tip away, okay? So the question is, you know, you have this massive object, right? And you're trying to perturb it away from its equilibrium point, okay? So one thought experiment to think about is, let's say you have your friend, this is what's called, everyone knows what a merry-go-round is, right? Okay, it's, you go to the, you know, the park, and it just goes around and around and around. And so you can buy a ticket and you can sit on this horse here, okay? But just because you're sort of, you know, interested in physics, you decide to tie a little rope to your friend, a very light thread to your friend. And your job is to pull your friend off the horse with a very thin thread, which if you pull too hard will break, okay? So this thing is going around. So what should you do to pull your friend off the horse? What do you need to do? You have a little thin thread that you can tie to their pinky. And how are you going to get your friend off the horse as they're on this merry-go-round? What happens if you just stand there? What's going to happen to the string? If you just pull on the string and just stand there. Anyone?
Are you also on the merry-go-round?
No, you're on the ground. Yeah. If you pull on it, it's going to snap. So what do you need to do to pull that person off the merry-go-round?
Walk slightly slower than the rotation of the merry-go-round.
Slightly slower. Yeah. Okay, why would you go slower?
So that you're constantly pulling them or
right.
pulling them away, but the string is.
Okay. So what is your frequency of rotation? Is it the same as theirs, or faster or slower? A little less. Why not exactly the same?
Because then you just be moving exactly what they're not.
Yeah, but you keep pulling them, right? You're allowed to pull them, right? Yeah. So now that I say you can pull them, you can add a little bit of tension to that. What frequency should you be at? Same. Yeah. Okay. So that's the idea, that basically, if you have this massive, you can only exert a tiny force. So this B1 field is very, very tiny. Okay. It's only on the order of a Gauss. Okay. Compared to this huge field, which is, you know, many tens of thousands of Gauss, right? So you've got to apply what's called on resonance. Okay. So that's the first concept that we need to talk about. So for example, this is representing the magnetization. This is going to represent your B1 field, okay? So if you're on resonance, it will tend to follow, and that will sort of pull the magnetization down wherever you want it to go, okay? Essentially, it wants to process around this field, but if you add a field here, it also has a tendency to want to process around this field too, right? And so that precession is what sort of you're taking advantage of. Now, if you go wrong at the wrong rate, so let's say I gave you a slightly stronger string, but if you're going at the wrong frequency, it's just not going to be as effective, right? And so that's what happens here. If you apply the wrong frequency, it just doesn't perturb the spin. The person just sits there, okay? So the first thing we need to know is that when we design these systems, my RF excitation has to be at the right frequency as the spins. Okay. Now, basically, to think about things spiraling down is sort of, that's a lot to keep track of, right? So oftentimes in physics, we'll go to what's called a rotating frame of reference, right? Which we're all familiar with because we're all right now on a rotating frame of reference, right? I'm not thinking about the Earth going around, right? We're both on the Earth, so we appear static to each other. Same way, if you are here on the merry-go-round and running around at the same rate as the merry-go-round, then from your point of view, the person just looks like they're standing still, right? And you're just pulling them towards you, okay? So that's essentially what we do when we go to the rotating frame of reference. We imagine we're going along with the spin, okay? And then in a rotating frame of reference, then it just appears that they're just coming right back down. So we don't have to think about this spiraling down, okay? So in the laboratory frame of reference, things are very complicated, right? Because we have to think about this whole spiraling down business. So in MR, we always are in the rotating frame of reference, typically such that this magnetization simply appears like it's going from here down to here. And now what we're introducing is the notation theta equals 90 degrees. So theta is what we define as the flip angle. Okay, so when you go up to an MRI scanner, we'll show some examples later. There's generally a place for the technician to type in flip angle. Okay, that's what this is. The flip angle is how much you're tipping that magnetization. Anywhere from 0 to 180 is fine. 90 degrees tends to be a very common flip angle. Okay, but lower flip angles are also common. And 180-degree flip angles, as we'll see later, are also very useful. Okay. So basically, that flip angle is what's the angle that you're perturbing this away. Okay, so that flip angle is essentially given by the frequency of precession of the spin. Okay, so the spins precess around any magnetic field. Okay, so they also precess around this little field. And so the frequency of precession, remember, is just given by gamma times the magnitude of the field, V1. Okay, and so this is in radians per second. So if we integrate over some amount of time, then we get the total flip angle. We integrate that frequency over time and get the flip angle. All right. So let's take an example. I think this will be the last. We'll just do this example and then we'll end for today. So this is an example of a pulse that is actually used in practice. So I turn on this amplitude V1 and I have it on for 400 microseconds. Okay, and I want to achieve a pi/2 or 90-degree flip angle. Okay, so then it turns out, obviously, integral of this, right? So the theta is equal to gamma B1, and that's just equal to gamma times the B1 times my tau, right? That's just the area, right? And so I can just solve the equation for B1, and if I do that, I get 0.1468 Gauss. So you can sort of see the units here are essentially on the order of the Earth's magnetic field. So these B1 fields are very small fields, but they're effective enough because when we apply them on resonance, they're sufficient to tip the magnetization to where we want it to go. Okay, so that's the last slide we'll do for today. Any questions before we end for today? Okay, so Monday is first project presentations. We'll send an announcement about this, but be prepared to present on Zoom because that way we don't have to spend time changing cables and everything. So basically, we just change sharing of screens. So even if you're doing it in person, yeah, for the live groups, just you're going to present it live, but you're also going to be on Zoom at the same time. Okay, so that way we can not spend time switching, and we can also record it, and people can join remotely if they want to. And then there will be a homework assigned this week, but you'll have 2 weeks to do it. So you can decide when you want to do it. There'll be some, it's not going to be a 2-week homework set. It's more like a 1.5 week sort of homework set. So, with some fun exercises to do. And then I'll send an announcement next week. There will be, as for the MRI part, there will be pre-lecture quizzes, typically 3 or 4 questions that just, if you've watched the previous lecture or listened in, should be fairly easy for you to do in a few minutes. If not, then you'd have to go back and review the lecture. Okay. So I think that's it for today. Anything online? No. Okay. So we'll see you next week for the project presentations then. Okay, thanks.